Welcome to The Explainer. Today, we're going to tackle a component that's in pretty much everything electronic, the diode. And we're going to do it in a cool way. We'll start with this super simple, perfect idea of what it is, and then, layer by layer, we'll add in the messy, real-world physics to see how it actually ticks. Sound good? Let's jump in.
Okay, so to really get what makes a diode so special, let's first think about something you probably already know, a resistor. A resistor, it's basically a two-way street, right? Current can flow back and forth, no problem. But a diode? Nope. That's a strict one-way street. Think of it like the bouncer at a club. It only lets traffic flow in one direction, period. And that's really the heart of it. A diode is the simple two-terminal thing with one incredibly powerful rule. Electricity can only go one way. And that simple property? That's the secret sauce in, well, everything. Your phone charger, your car's radio, you name it, it's probably got a diode in there doing this exact job.
But you know, there's always a catch, isn't there? See, with a resistor, life is easy. The relationship between voltage and current is a nice, predictable straight line. You probably remember it, Ohm's law. With a diode, though, it's a curve. And that nonlinear behavior, it makes the math a real headache. So what do? Well, to make their lives easier, engineers came up with some clever shortcuts. Simplified models.
And we're going to start with the absolute simplest model you can imagine. We're talking a perfect idealized world here. Let's just pretend for a minute that a diode is nothing more than a perfect little switch.
So, in this perfect little fantasy land, our diode is super simple. It only has two modes. If you point the voltage the right way, click, the switch is on. It acts just like a piece of wire, zero resistance. But if you try to reverse the voltage, click, the switch is off. It becomes a perfect wall, blocking every last bit of current. On or off. That's it.
Okay, let's put this perfect switch idea to the test with a basic circuit. Imagine we've got a 10-volt source, a 100-ohm resistor, and our ideal diode. Now, since the voltage is going in the right direction, our diode just flips on, right? It becomes a closed switch. Basically, it disappears and acts like a piece of wire. And that makes the math super easy. We just pull out our old friend Ohm's law.
And boom, there's our answer. In this perfect, ideal little world, we get a nice, clean 0.1 amps of current. So simple. But I think you know where this is going. That's not the whole story, is it? The real world is always a little messier.
Yeah, reality is definitely not that perfect. So let's peel back that first layer of simplicity and add in a little bit of real-world physics. To do that, we have to introduce a new idea, and I like to think of it as a tiny little entry fee, or a toll you have to pay. This toll has a name. It's called the threshold voltage. See, a real diode doesn't just turn on the second you apply a little positive voltage. No, that voltage has to be strong enough to overcome a small barrier first. You've got to pay the toll, and only then does the gate actually swing open to let the current flow.
And what's really cool is that the size of this toll, it completely depends on the material the diode is made from. For almost all the diodes you'll find today which are made of silicone, that toll is about 0.7 volts. But if you were working with older tech with diodes made of germanium, that toll was much smaller, only about 0.3 volts. Kinda neat, right?
Okay, so let's go back to our circuit and see what this toll does to our calculation. Same setup, 10 volts, 100-ohm resistor. But now, we're using a real silicon diode. So right off the bat, the diode itself uses up, or consumes, 0.7 volts just to open that gate. That means our 10-volt source doesn't have 10 volts to push current through the resistor anymore. It only has 9.3 volts left to do the work. And check that out. That one little change makes a real difference. Our new current is 0.093 amps. Now, it might seem like a small change, but think about what we just did. By adding just one piece of real-world physics, our model got way closer to what actually happens.
Okay, we're getting really close now, but we're not quite at the finish line. There's one more layer of reality we need to account for. Think about it. Once you've paid the toll and the gate is open, the road you're driving on, well, it isn't a perfectly smooth superhighway. Right. Every road has a few bumps. For a diode, those bumps are its own internal resistance, what we call bulk resistance. It just comes from the simple fact that it's made of a physical material. So even when the diode is fully on, it's still putting up a tiny bit of a fight against the current. This gives us our second and much more accurate model. All right, let's run the numbers one last time with this final piece of the puzzle. We still have to pay that 0.7 volts toll. That doesn't change.
But now the total resistance isn't just the 100 ohm resistor. We have to add the diode's own internal resistance, say a typical 25 ohms, into the mix. So the total opposition to the current is now higher.
And there we have it, 0.074 amps. You can really see the difference now, can't you? By accounting for both the entry toll times the bumpy road, we've arrived at the most realistic, accurate prediction of all our models. We've really built up a solid understanding from that simple switch idea.
So let's just pause for a second and appreciate what we did. We built a pretty awesome approximation of how a diode works, right? Step by step, we started with a perfect switch, then we added a voltage drop, then we added a resistance. This whole approach, using these simple straight line rules, is what engineers call a piecewise linear model, and it is an incredibly powerful tool for analyzing circuits. But, of course, that begs the big question. How good is our model? How does this step-by-step straight-line approximation compare to what a diode actually does in the real world?
Well, here's the big reveal. The true behavior of a diode, it's not made of sharp corners and straight lines at all. It's actually a beautiful, smooth, exponential curve. All those models we just worked so hard on, they are fantastic, clever approximations that make the math manageable. They're our way of taming this complex, curvy reality.
And if you look at this real curve, you can see it's really split into three main zones. You've got the forward region, that's where the diode is on and the current just takes off like a rocket. Then there's the reverse region, where it's off, and just a tiny, almost undetectable amount of current leaks backward. And then there's the breakdown region. This is the danger zone. If you push way too much voltage backward through it, you can destroy it.
So, just to wrap up our journey, here's how it all breaks down. We started with the ideal model, a perfect switch. Super simple, but not very accurate. Then we added the voltage toll, which got us to a medium level of accuracy. And finally, we factored in the bumpy road of resistance, and that got us our most accurate model. See how each layer brought us closer to the truth?
You know, this whole process reminds me of a famous quote from the statistician George Box. He said, "All models are wrong, but some are useful." And that just nails it, doesn't it? The point of our diode models wasn't to be a perfect 100% accurate copy of reality. The point was to be useful enough for us to understand, analyze, and build real circuits that actually do what we want them to do.
And really, this way of thinking, of starting simple and layering on complexity, it goes way beyond just electronics. It's how we understand so many things, from physics to economics. We start with a simple idea, and then we add in the nuances, the exceptions, the real-world stuff. It really makes you think, doesn't it? What other perfect ideas do you have in your head that are maybe just the first, simplest version of a much deeper, more fascinating story?